Hi all and welcome to this week's game features video. So this really follows on from the broad video we had last week on the structure of your game and how to take an overall approach as to what is the game look within the game. Now we're going to look in a bit more detail at some of the specific things you need to think about when you're coding a game. So I said in the assignment brief that it had to either be physics, which you can do with use of a physics engine, be networked. I know that's fake, I'll explain why in a minute. Have a level creator or use artificial intelligence as the term is used within games programming. Okay, so what I'm going to do in this video is take you through each of these in turn and talk a little bit about them. I have to admit, I am going to talk a bit more about artificial intelligence. There's two reasons for that. The first reason is there isn't really AI libraries out there, so if you're doing AI, you're going to have to do it yourself. The second is, if I'm honest, it's what I do. It's the part of games programming that really excites me. I have a PhD in artificial intelligence. So if I'm honest, I show a bent towards it, and I think it's just worth telling you that. So first of all, let's have a look at physics engines. So physics engine, most of you will probably be using it for collision detection. You may be using it for some other things as well. So you might, for example, have a ball bouncing around in your game and you want gravity applied to that ball. So that's different to collision detection. But given that most of you will be using it for collision detection, when we're talking about it, I think we should start there. So typically, collision detection in games is carried out into two steps. And interestingly, our guest speaker on Friday spoke a little bit about this. So the first thing is to determine which pairs of shapes need to be tested for collision. So this is called the broad phase. And what you end up with is just a list of at any given time, any frame, how many things you need to how many things you need to test to see if a collision has occurred. Then what you have is the narrow phase, where you actually just step through this list and say, okay, which of these ones has been hit? So I'm thinking about collision detection, you've got your broad phase and your narrow phase. I have to admit, the easiest way to do this is to use a library, and that is absolutely fine. Integrating a library with your code will actually require quite a lot of coding on your part, so that's okay. You can do this if you wish by yourself. If you're doing it without a library, I suggest choosing a point in each object or putting a box around the object and looking to see if a collision has happened in there, seeing if these touch in some way. If you're ever in doubt as to how big the bounding box should be or the point should be generous to your player. So what we're trying to do is not annoy our player. If they don't feel like they've just been shot and they die when an NPC tries to shoot them, they're going to get really, really annoyed by this. On the other hand, if they feel they've shot an NPC and yet they don't die or they don't get hit, they're also going to be really annoyed by that. So the best thing to do, at least for a starting point until you do some play testing, is make your bounded box on the actual player character small and make one of the NPCs slightly bigger. And that way, you're being slightly generous to the player and you're less likely to annoy them. It's likely to feel more fair to them. If, on the other hand, you're making a multiplayer game, you want to make sure that everybody has exactly the same setup. So the bounding boxes of all characters are the same, unless you have something like an easy mode or a children's mode. And then in that case, you can make the bounding box of the other players larger and of the people with the easy mode or children's mode a bit smaller. See what I'm saying? You can really adapt this to make your game a better experience for all involved. In general, for physics, if you're not just doing collision detection, if you're doing physics in more detail, I suggest using a library. Unless you want a major coding and mathematical challenge, you'll be reading about physics engines in the book this week, and you'll see they are quite mathematical, and you have lots of extra time. Last year, a few people actually did decide to implement their own physics engines, and they were fantastic. They were really great. So it is something you can do if you want to, but it's not something you have to do if it's something that will be challenging for you. So that means if you're not implementing your own, you will have to choose a physics library. How do you do that? Well, the first thing is probably to think what works with your hardware that you're using and your games engine. If there's one built into your games engine, you really got to have quite a good reason not to use that one. Okay. The second thing to think about is how will it fit with your code? How will it fit the code you've got so far? We'll be looking at design patterns next week, but just as a bit of a heads up, the adapter design pattern really can be very useful here. So we're looking at design patterns, you might want to consider the adapter pattern. Once you've found one that works with your hardware software, you might still have other choices to make. So then it's thinking about, what do you actually need your physics library to do? Do you need to change gravity? Do you want realistic gravity? Most games, I have to say, special platforms don't really have realistic gravity. You can jump a lot higher than you usually could. If you've got a ball, it tends to just bounce around. It tends not to bounce and then and land on the ground. Sometimes you actually want heavier gravity to only like small jumps, small bounces. That's really worth thinking about. Does it need to make real-time calculations? Does it need to be fast? Because some physics engines work behind the scenes and do calculations ahead of time that may be required, and so the speed of the physics engine doesn't really matter. But in some games, they'll actually be updating the physics every frame. So you need it to keep up with your game life. You need it to keep up with the frames per second. So you need a really fast physics engine. So it's worth thinking about that. And in general, think about how much does it need to mimic or otherwise the real world? Is it kind of cartoon physics you're looking for? Or is it completely real world physics? Because that makes a difference to choice. As an example, one physics library which I have to say is the one I use the most and I quite like is Box2D. The reason I've linked to the Box2D manual here is what they've got is a really good overview of everything that their library does. And so it's a good example of what you can get from a physics library and how physics libraries work. So you've got an example of that, and I suggest it's a good place to start. Okay, so that's all for our physics. What if you want to be networked? Now, I know be networked is really very vague, okay? It's deliberately vague because I wanted to give you scope to think about the best way to do it in your game. So it could mean local multiplayer with some sort of device-to-device connection. It could be online single player, so it could be an online game. It could be online multiplayer. Or it could be Bluetooth connectivity. So last year there was actually one game which connected phones together via Bluetooth. That was absolutely fine. I put ... here because there's other things it could mean. And I'm really happy for you to come to me and say, okay, I think I'm making a networked game and here's how I'm doing it. Does that count? The chances are I'll probably say yes. Okay, so think about this as vague a way as you want to, and there's lots of different things it can mean. And I'm happy to discuss it. There are tutorials for most of these ways of being networked in the Padlet. So do have a look at the tutorials, and there's probably there one for you. So the next thing we've got to think about is level creator. Okay, so there's actually 3 ways to think about level creator. You can think about it as a way that allows you as a programmer to easily create levels. So it can be something that's actually only allows you to drag and drop things into levels, and then you compile it, and that's the levels you get for your game. That's one way, and that does actually count as a level creator. It can be to have automatically or what's called procedurally generated content. Roguelike type games are usually procedurally generated, so that's definitely creating a level. It can also be a mechanism for the player to create their own levels. So in particular, if you do one well, then it can often become 3. So if you've got a way where you as a programmer can easily create levels, you can often actually give that to the player to allow them to create their own levels, and that can really add a depth and complexity to your game. For this module, all of the above count as level creators, no problem at all. And there's a link to the tutorials for this in the Padlet. So I think the way to really do this is to look at the Padlet and look at the tutorials and work your way through. So the last thing you might want to do with your games is artificial intelligence. Okay. So the first thing I want to tell you about artificial intelligence in games is it's really different to mainstream AI. You have probably heard, if you've not been living under a rock, of machine learning, deep learning. Those sorts of things are mainstream artificial intelligence. Actually, if you go to a Games AI conference, there's not a lot of that mentioned. There's a little bit, some people do talk about this. What they really mean when they talk about artificial intelligence in games relates to the behaviour of the non-player character. So how do you make the non-player characters seem to the player to be more intelligent? And actually, in modern games, we're beginning to look at using machine learning and deep learning to do that, but that's more a tool to make it more intelligent rather than the fact that the AI itself is those algorithms. So the difference is AI in games is about what you do with it. Artificial intelligence as like a research field is about creating new algorithms and creating new things to do. Hope that makes sense. So one of the first intelligent games, and I think actually still one of the most clever ones in many ways, is a game called Pac-Man, which hopefully you've all heard of. What I'm about to talk about comes from the Pac-Man dossier, and I put a link there. And what we're really going to talk about is how does the AI in Pac-Man actually work? So on the next slide, I'm actually going to show you a very quick video of Pac-Man working. I'm doing this because there might be some of you who've actually never played Pac-Man. If you've not, I suggest going and having a play. You can find it online nowadays. And just thinking about how do the non-player characters, or in this case ghosts, actually operate. What algorithm is going on behind? Notice the ghosts have names if you've never noticed that before. So as you're watching this, remember you're looking to see what are the ghosts doing, how are they behaving, and why are they behaving that way? What algorithm do you think is behind them? Okay, so they finished that level. I have to say, they are far, far better at playing Pac-Man than I am. This is not me playing. It's not a game I've ever mastered. Okay, so how does this actually work? Well, the first thing to note is every single level and platform in Pac-Man, Pac-Man, has exactly the same layout. You always start with the same maze, for want of a better word. Okay. Also note that currently only one ghost is in the actual maze. So only one ghost starts in the actual maze, it's the red one, called Blinky. Others are inside a small area in the middle, which is often referred to as the ghost house. The ghosts only return to this area if they're eaten by an energized Pac-Man, so Pac-Man's eaten a pill, or as a result of their position being reset when Pac-Man dies. The ghost house is otherwise completely inaccessible. In particular, note that Pac-Man himself can never get into this ghost house, so it's just an NPC area. The ghosts always move to the left as soon as they leave the ghost house, but they may reverse direction almost immediately. So what's really impressive about Pac-Man is that the ghost AI is very simple and short-sighted, which makes the complex behaviour of the ghosts even more impressive. Ghosts only ever plan one step into the future as they move about the maze, so only ever looking one step ahead. Whenever a ghost enters a new tile, it looks ahead to the next tile that it will reach and makes a decision about what direction it will go in when it gets there. So it's only ever looking one tile ahead, and at that point it's saying, okay, what direction do I turn in? It's even more simple because ghosts may never choose to reverse their direction of travel. So they carry on going in one direction unless there is a junction, they carry on in that direction. The implication of this restriction is that whenever a ghost enters a tile with only 2 exits, it always continues in the same direction. So if there is no choice of junctions, always carry on. There is one exception to this actually, which is whenever the ghost changes mode, they're forced to reverse direction, but I'll get to that in a second. In the main mode, main game, if it's not a change of direction possible, if it can only go straight ahead, it will carry on going straight ahead and never reverses direction. This means that quite cleverly, moving decisions are very rarely needed. So if you look at this map here, you'll see the green squares and the yellow squares. These are the only times that a moving direction is needed. It's the only time when it's possible to change as a junction to change direction. Okay, which means that most of the time it's really quick to keep the FPS because you know that you're just going to carry on going in the direction you're going. The ghosts are always in one of 3 possible modes. They're always in chase mode, scatter mode, or frightened mode. How long they're in each mode for varies from level to level. So in level 1, they actually scatter for 7 seconds, then they chase for 20 seconds, scatter for 7, then they chase for 20, scatter for 5, then chase for 20, then they scatter for 5, then they switch to chase mode permanently. Okay. And this is how they actually show the difference between levels. So in level 1, they scatter for 7, chase for 20. That scatter time will get lower and the chase time gets larger as the levels get more difficult. And that's the only thing that changes the difficulty between the levels. What do I mean by scatter mode? Well, in scatter mode, what they try and do is head towards a square on the board. And you can see, for example, that Inky the pink ghost tries to get to the top left-hand square. It can't get there because it's out with the maze, so there's no exit, there's no way to get there. So what it ends up doing is going around in that square just below, as shown. The same way, the red one, top right, can't get there, so it ends up going around in the pattern shown, and the yellow and the green are the same down at the bottom. So let's look now and think about what each ghost actually does in chase mode. So the red ghost, Blinky, does not start in the ghost house. Blinky's target tile in chase mode is defined as Pac-Man's current tile. So what it's trying to do is directly reach Pac-Man. So if it's got a change of direction to make, if it's at a junction, it will go in whichever direction Pac-Man is. At 2 defined points in each level, which are based on the number of dots remaining and how many have been hit by Pac-Man, the speed of Blinky increases by 5%, and his behaviour in scatter mode changes. So instead of scattering at those points, he remains in chasing mode. Okay, he's the only ghost that can get faster as the game goes on. He's the only ghost whose speed changes. The pink ghost, Pinky, starts inside the ghost house, but always exits immediately whenever you start. The target tile in chase mode is determined by looking at Pac-Man's current position and orientation and selecting the location 4 tiles straight ahead of Pac-Man. Apart from, and I think this is amazing, this is one of the most successful games of all time, actually it has an error in it, people. So an overflow error in the game's code causes Pinky's target tile to actually be set as 4 tiles ahead of Pac-Man and 4 tiles to the left of him when Pac-Man is facing upwards, so only at that point. And that was a complete error in the code and one that people only found later on. So it just shows you that how successful you can be even if you do make small errors. So here's a diagram of this. Most times it's 4 squares ahead of Pac-Man, but we've got that error where it becomes 4 squares ahead of Pac-Man and 4 to his left when Pac-Man's facing upwards. Okay. The next ghost we've got is Inky. So Inky's the blue ghost, remains inside the ghost house for a short time on the first level, doesn't join the chase until Pac-Man has consumed at least 30 dots. He uses both Pac-Man's position facing as well as Blinky, the red ghost position, to calculate where to go. Okay, how does it work? So you start by selecting the position 2 tiles in front of Pac-Man in its current direction of travel. From there, imagine drawing a line from Blinky's position to this tile, then doubling the length of that tile. So what we're doing here is we're using both the red ghost, Blinky's position, and we're using Pac-Man's position. The idea is really it should feel as if Blinky is coming in behind. So the red ghost is always chasing him and the blue ghost is coming from the opposite side. The orange ghost, Clyde, has 2 separate modes which are constantly switched back and forth based on how close he is to Pac-Man. First, calculate his distance from Pac-Man. If it's further than 8 tiles away, his target is identical to Blinky's, and that is it's trying to get directly to Pac-Man and it uses that as a target. If it's less than 8 tiles, then it actually does exactly the same as it's a scatter mode. It tries to get to that bottom left-hand corner, which it actually can never get to see what effect that has. So more than 8 tiles away, and you can see therefore it's trying to head directly for Pac-Man. So at the end of that row, it's going to take a left-hand turn. If it's closer than 8 tiles, it's going to try and head to its corner down there. Okay. So that's it. Now you have seen what the algorithms are. Try and rewatch the video and see if you can see the ghost behaviour. You might even want to try and replay back Pac-Man and see if it's any easier knowing what those rules are. I should tell you, by the way, that I don't think it actually is. I think even though you know what the rules are, because you've got 4 ghosts all working together in different ways, it's just too hard to really think about the algorithm while you're playing. So it'll be interesting to see if your match is the same. What can we learn from this? Well, this is surprisingly close to modern game artificial intelligence. You get a really complex behaviour by taking lots of simple algorithms and putting them together. So modern research is really about building up more and more complex rules. And the way we actually do that is often based on how humans solve problems. Okay, so if you were trying to chase somebody, what you might do is you might follow them directly, or you might try and find a different route to them. That's exactly what's happening in the Pac-Man's ghosts. Okay. I very, very rarely say things like this, but if you are doing AI in your game, if you do something that's sophisticated and works as well as Pac-Man, you will get an A for that aspect. So if you've got 4 different non-player characters with 4 different algorithms that makes them look intelligent as if they're working together, then I can guarantee you will get an A. And that's something I very rarely say, but I think it's worth saying that is sort of the gold star almost for this aspect. Okay, I hope that's been useful, and I will see you all on Monday.